Welcome back, guys. This is review session, part 2. Okay, so now we're going to address two laws. First one is law of superposition, and the second one is the law of original horizontality. Okay, so let's address the law of superposition and law of horizontality, original horizontality. So let's look over here. What the law of superposition states is that the oldest rock is always found at the bottom, and it gets progressively younger as we move to the top, as long as these are undisturbed rock layers, and this is very much undisturbed. The second law, which is the law of original horizontality, states that all of the rock was originally laid horizontally. Okay? Now if we come over here, we can see that this is representing some kind of bending, folding, and tilting event. But we know that these rocks had to be laid just like these guys over here. Okay? They were at one point in time nice, pretty, horizontal layers. But due to pressure, due to events on the earth, plates pushing inward, we get a bending, folding, and somewhat of a tilting event that occurs. So this is showing us superposition, oldest to youngest. Horizontality, they're in nice little rows. Okay? And when we think of law of superposition, I do want to add one more thing. When we look at the fossils, if the fossils down here, if I look at it age-wise, this is the oldest rock layer. Any fossils in here would also be the oldest fossils. And as I get up progressively, it's going to get younger. Okay, so the next question we have is, what are tree rings and ice cores, and what kind of information do they tell us? Okay, so let's look at ice cores and talk about that. Now obviously what's in my hand, which is my hand, this is just an ice cube from my freezer. And as you can see, this is my thumb, you see all these little dots and holes. And what these little dots are their bubbles of trapped air. Okay, so if this was actually coming from the Antarctic, these little bubbles would contain gases, and these gases would tell us how the atmosphere has changed in terms of oxygen, in terms of nitrogen, how they've changed over time. Okay, so when we're thinking about that ice core, I want you to envision this nice little cylindrical piece. And this would be what's actually cored out of the ice. And what I've drawn in here is just kind of showing you differences and what the scientists would be looking at. So they would be looking within this layer, and we notice perhaps maybe there's just a ton of black ash or something. And what that could tell the scientists is at this point in time in the geologic history, there may have been a massive volcano. And that volcanic ash is spewed up into the atmosphere and eventually lands in areas like this where ice would accumulate. And this could tell us of a widespread volcanic activity that may have led to a massive extinction. We also see something maybe in here where we have the bubbles like we talked about, and they would take and analyze that air simply to see what the atmospheric conditions would look like. So this gives us a piece of our puzzle. Over here I've made an attempt at drawing a tree ring. So we know that if we took our little tree like this and we cut the tree ring is taking this piece right in here. And that's what that is. Right, like that. Okay? What the tree ring tells us, well, first off, obviously you can tell age from a tree ring. So we know how old the tree is based on how many rings there are. But more importantly, when we want to connect it to this ice core, is looking at the thickness or thinness of the rings. The thicker the ring tells me that this tree got lots of water. The thinner the ring tells me it didn't get as much water. So when we look at events in history, this could tell us that there may have been a time of plentiful rain, maybe possibly flooding in some areas. This could tell me of droughts. So I could connect possibly the droughts to mass maybe not extinctions necessarily, but lots of plants or animals that started to die off because we know in this time period there wasn't a lot of water available. This can tell us that life was good. And if we start looking at those really, really, really old trees that have huge rings, that can give us information. So between an ice core and a tree ring, they provide us information about the climate, they provide us information about volcanic events that we see in the ice core, and we can take this information, we can look at fossils, and we sort of piece it together to make a story. Okay, the next question we're going to look at is naming the 3 types of boundaries, and then what will form as a result of these boundaries. Alright, so let's talk about these boundaries. So we're going to do a little dancing, okay? Let's do the divergent boundary.
because they go away. And the convergent boundary, because they come towards each other. And then we have the transform boundary, and they slide past each other.
Alright, so while I know you all enjoyed my rock and dance moves, let's actually get a little more technical. So this is a convergent boundary, and we have two types, okay? We've got continental, and then continental-oceanic. They're both doing the same thing. They're both coming towards each other. This just happens to be two pieces of continental crust. This is a continental crust and an oceanic. So let's look here. We've got land, obviously, and these two pieces are converging on each other. And as they come towards each other, they're going to cause mountain formation. So we can imagine our fingers coming together and pushing upward. With this one, the oceanic crust is approaching this continental crust. It is coming towards it, however, it's going to do something called subduct. And what subduct basically means is they're still coming towards each other. This piece of crust actually goes below. And what's going to happen is it's going to melt down here in the magma chamber. And we might see eventually the formation of a volcano and a volcanic set of mountains along the coast. But they're still coming, they're still converging, just like these two are. This one just is going to sink below this one. Alright, so the next type of boundary is the divergent boundary, and as we did with our hand motions, what it means is that the plates are now pulling apart. And they actually start pulling apart. I'm going to erase this real quick, because when they start to pull apart, it's almost like they're tilting. What's happening is we've got a magma plume down here, so we got some magma down here, a magma chamber of some type, and it's forcing magma up here, and therefore causing, it's basically pushing these things apart. And this magma is just piling on. And so what we start to get are things called ridges, okay? And there's a really large ridge called the Mid-Atlantic Ridge that runs right down the center of the Atlantic Ocean. And what it is it's a spot where the boundaries are actually, a plate boundary is, and this is actually pushing apart. And these start to shift this way. And this ridge will continue to shift. And the magma will just continue to pile up, and that plate will continue to move apart. Okay, the third type of boundary is the transform boundary. And so with the transform boundary, what we have is we have plates now shifting in opposite directions. So they're literally going to be scraping past each other. And when we have this scraping, because we can imagine scrape, what we start to feel is something like an earthquake. Okay? And we know, if you know anything about earthquakes, I mean, obviously we can get them in North Carolina. There's nothing that says we can't, because we do have plates meeting up like this. But you tend to hear the most about it in places like California. And so an example of it that you may be familiar with is the San Andreas Fault. And the San Andreas Fault is a fault line that's created as a result of this transform boundary. So when that scraping action happens and you hear about when you hear about earthquakes in California, you may be thinking, or it may be as a result of this boundary at the San Andreas Fault. Alright, so let's look at the next question, which is what are the three types of rocks, and then how are they formed? Alright, so let's start to talk about the three rocks, and then we'll talk about the cycle. So the first type of rock that we have is sedimentary rock, and you're going to see this with sandstone. The second type of rock is igneous, and we see this with obsidian, which is very glassy, as well as granite, which is very lots of crystals within it. The last type is metamorphic, and this is something you'd see in marble. So when we think about a cycle, we have to think that there is movement within that cycle, and we've got these arrows to kind of give us movement from one form to another. So whether we're coming this way from metamorphic or we're coming this way from igneous, the only way we're going to get a sedimentary rock is by undergoing these processes of weathering, erosion, deposition, compaction, and cementation. Now, over on this igneous side, instead of rewriting all this, I'm just going to go WEDCC, which means the same thing. So in order to go from igneous to sedimentary, I have to weather, erode, deposit, compact, cement, or metamorphic to sedimentary. I've got to go through the same thing. Now we're moving from sedimentary to metamorphic, or igneous to metamorphic. There has to be some kind of heat and pressure And when we talk about heat and pressure, we're not just talking about, ouch, that hurts. We're talking about intense heat. And pressure, we're talking about the whole pressure of the planet. Think in those terms. And that's going to get us the formation of a metamorphic rock. And the last but not least is that igneous rock. And in order to get igneous, there's going to have to be a melting and cooling event. So this rock is melted and cools and becomes igneous, or this rock melts, and cools and becomes igneous. So this is the rock cycle. Remember, every rock can become any other rock. It just depends on the conditions.
All right. So the next question is talking about the geologic time scale. So first off, we want to know what it is, and then we want to know what it tells us about life on Earth.
Okay, so the final question was talking about geologic time, and I decided to bring out the clock because I think it's sometimes the easiest way to look at it. So we did this in class, but just as a review, we're going to set Precambrian time. So I'm going to go ahead and put that little dot in the middle of the clock. Okay. Precambrian time, we start at the midnight, we go all the way around till we hit about maybe 1052, 1053-ish. That means all of this time in here. All of this is Precambrian. Precambrian, we have the beginning of Earth. We have a lot of movement within Earth, volcanics, eruptions, maybe some small bacteria, small single-celled organisms, but not a whole lot's going on in here. Okay. From here, we move into the Paleozoic, and the Paleozoic is going from about 53 to maybe about 57. Okay, so right in here, this is the Paleozoic. And with the Paleozoic, we sort of see an explosion of life. So we see the beginning of reptiles, we have Pangea action, maybe potentially starting up in here and sort of ending in here. From here, we go into the Mesozoic, and the Mesozoic is going to go from about 57 to about 59. So this is the Mesozoic. The Mesozoic you can pretty much remember as the whole dawn of the dinosaurs. The dinosaurs come in, they thrive, and they go extinct within that Mesozoic. And this final piece of time, so from 59 to 60, so for just 1 minute, this is the Cenozoic. And this is the current era that we are in right now. The Cenozoic began because the dinosaurs went extinct. So once the dinosaurs go extinct 65 million years ago, we move into the Cenozoic, and mammals take over and sort of flourish within the planet. Now, when we look at geologic time, all we're doing is we're putting all the events that have happened on Earth, and we put them together with all the life events that have occurred. So the Earth events and the life events. And we, taking this same approach, we just create a line. Okay? And we break that line up. So we have Precambrian, Paleozoic, Mesozoic, Cenozoic. So a lot of time here, getting smaller and smaller, but this is the point in time where there's lots of life. When we think about human beings kind of come in right in here. So we're very much at the end of the timeline in terms of this entire geologic history. Remember, the Earth is 4.6 billion years old. Okay, it's a huge amount of time. And with that time, a lot of stuff doesn't happen for this much time, and then all of a sudden it does. And this is the explanation of geologic time. Okay guys, so our session has ended. So hopefully you have answered any questions, and I know Danny, you have been very intrigued by everything we've learned about. So, yes I have. Alright, so please make sure that you have studied really, really hard for this test, and if you have any questions that you come see your science teacher. If you're coming to see me, just make a scheduled time and we can go over any material that was covered, anything that you still are uncertain about.